Okay. I assume everyone's progressing well through the homework. If you have any questions, of course, you can email me. I don't know if you've noticed this, but there is an office hour posted for Friday mornings at 10 a.m. So I always open up the Zoom, and if you need to join for questions, then I'm in there in the Zoom room waiting for you guys to show up and ask your questions, and I'll be happy to answer whatever I can. So if there aren't any questions, let's start chapter 3. And chapter 3 is the topic of this is the asymptotic expansions of integrals, and we're going to cover 2 methods today, partly or completely. The first method is going to be the method of integration by parts. It's the easiest to understand, the easiest to use, and it works when it works. It doesn't work all the time. It doesn't work for a very broad class of integrals, but we'll see that it works for some. You'll kind of get the idea of what it works for and what it doesn't. So let's recall what is integration by parts, just in case you're really rusty. So integration by parts means that we've got some integral that we want to deal with that has a complicated integrand, such that if we split this integrand into 2 separate pieces, we might be able to deal with these pieces on their own, but maybe not together, not their product. So I'm going to think about this integral as being v times du. So v times du. And I'm going to identify what are v and du. So I want v to be theta and du to be everything else. Now I'm going to integrate v, or sorry, differentiate v. So I just get, of course, dv d theta equals 1. So in the usual, so I'm not going to go through the rigorous theory of integration by parts. We're going to use the notation that we all know and love. We're going to pretend that derivatives are just fractions of differentials, and we can divide them up. So dv d theta equals 1 means that dv equals d theta. If I integrate this function u one time, then or this differential u, then I get u sine theta. So I can rewrite my integral then as I is equal to uv evaluated at the endpoints, theta equals pi, theta equals 0, minus the integral from the same limits, theta equals 0 to theta equals pi of u dv. So I had v du, now it becomes u dv. I know this is not very difficult. This is sort of trivial stuff. We can substitute back in for what are u and v. So u is sine theta, v is theta. When I evaluate at the endpoints, I get 0 in both cases. In the first case, if I put in theta equals pi, sine of theta is 0. In the second case, both theta and sine theta are equal to 0. Now that just leaves me with this integral minus. So remember, when I do integration by parts, I evaluate u and v at the boundary or the endpoints, and I have minus the integral of u dv. So that gives me my minus with u, which is sine theta, and dv, which is just d theta. So I've simplified my integrand by doing the integration by parts. This is the idea that we're going to invoke a lot. Actually, kind of. And I'll get back to that in a second. This, of course, can be integrated exactly. This is cosine of theta, evaluated at theta equals pi, and theta equals 0. The minus, well, the antiderivative minus sine theta is cosine theta. So I evaluated those 2 points, and I just get 2. 1, let's see, is that right? So Did I get the right sign on that? Cosine. Yeah, -2, right? -1 -1, right? -2. There should be a minus sign there. Okay. Now, this is, we're going to be, so I misspoke. So whenever we use integration by parts going forward, we're going to actually be making the integrand more complicated rather than less complicated. So we don't actually, so we observe that there's no way we can apply integration by parts to completely integrate this thing and solve the problem. And so what we're going to end up doing is actually making the integrand much more complicated over time, as you'll see. We're not going to simplify it as we did in this case to the point where we can actually solve for the integral. Before we get on to that, though, let's review a couple of definitions that we had back in chapter 2 that we're going to keep applying here in this chapter. Let's make sure we really understand these things. We say that F is asymptotically approximated, or G is an asymptotic approximation of F as epsilon goes to epsilon naught. Here we're going to be using as lambda goes to infinity. If and only if F minus G is equal to little o of G as, again, lambda going to infinity. So this approximation works by taking the difference and then showing that that difference is little o of this second function G. That difference is little o of the second function G, the approximating function. Now, this holds true if and only if F minus G over G goes to 0 in the asymptotic limit, epsilon goes to epsilon 0, or in our case, as lambda gets large, lambda goes to infinity. Okay, so this is the thing we're going to keep applying over and over again. And we say that F has an asymptotic series approximation. In other words, we say that this, let's start out with the finite case first. This finite series is an asymptotic approximation of F as epsilon goes to epsilon naught. Here we're going to be using lambda goes to infinity. If and only if, well, and this is how we write that. If and only if F minus the mth partial sum is little o of the mth asymptotic sequence member. Okay, phi m. So the F minus the mth partial sum is equal to little o of phi m. That's the mth term in that asymptotic sequence. I'm having trouble saying mth. Mth. Okay. So little o phi m for each m up to and including little n. And we say that this infinite series is an asymptotic series approximation of F, and this is how we write that. If and only if F minus the mth partial sum is equal to little o phi m as epsilon goes to epsilon naught. Again, we're going to be applying this for lambda going to infinity for every m, okay? So not just a finite number of terms, but an infinite number of terms. So that's what that represents there. Okay, so just put those in your back pocket. That's what we're going to be doing. Actually, this is the one we're going to be doing again and again. Yes, go ahead. Make sure.
You're missing the K under a phi again.
Oh, yeah, I know why, because I copied it. Could someone check, well, I'm pretty sure the answer. It's not missing in the notes, I think. Actually, I might have missed this one in the notes and in the slides because it was missing everywhere. So it may be in the notes, it may be missing. I don't remember if I got to it or not, but I'll try to correct that everywhere it's incorrect. Okay. So let's first start with an exponential integral. Actually, the way this is laid out in the notes, which are also posted on Canvas, and the way that this is laid out in the slide deck is a little bit reversed. I realized I was doing a simpler problem later, so I put the simpler problem first. So let's deal with this exponential integral. I of lambda equals lambda e to the lambda integral from lambda to infinity of e to the minus t over t dt. So you'll see that the method of integration by parts works best whenever the lower limit of an integral is that large parameter that I'm dealing with. And these exponential integrals are turn out to be a really good application of this integration by parts method. Now, this integral is related to this integral called E1, the first exponential integral. And E1 is defined as just this. And you encounter this in a lot of applications in physics and engineering. And so these integrals are tabulated and or the values of them for certain values, I guess. Actually, so these functions appear all the time. They also appear with different powers of t here, and we'll talk about those in a little bit. In any case, this is the same as I of lambda, except that it's got this difference of a prefactor in terms of lambda. So if we get an asymptotic expansion for one, we'll have an asymptotic expansion for the other. So let's have a look at this, this integral. And what we want to do is use the method of integration by parts to show that it has the asymptotic series representation given here. Now, for fixed lambda, here's a question for you. Does this series converge or not? So fixed lambda, does this series converge? What do you think? What do you think? Not really. Apply the ratio test. This is getting way too big. Okay. So just like it's not going to converge for any lambda, right? But if we if we make a partial sum and we don't go all the way up to infinity, we say we stop at, let's say, the term, this upper limit being 50. Then as lambda gets larger and larger, we get that partial sum is a better and better approximation. Remember, that's the nature of asymptotic series expansions. The series may not converge itself, but we get a nice asymptotic approximation, which means if we fix k and send lambda to infinity, we get better and better approximations all the time. Now, what we're going to do is use repeated integration by parts, and I think I do one step of this. I will. We're going to do one step of this to show you what's going on. And you'll notice that when we do this, the integrand is not getting simpler, it's getting more complicated. So the integrand that we're going to be working with is the one that's contained in here. So I claim that I can show an exact expression. I can show that for any capital N, a counting number, that I have I of lambda is equal to my n minus first partial sum, or partial sum up to term n minus 1, plus a remainder where the partial sum is here, and the remainder term looks like all this business. So notice that the integral that I end up with is definitely not simpler than the one I started out with. So after doing n or n plus 1 terms or steps of integration by parts, I end up with an integral that looks like this. The integral that I started with looks a whole lot simpler. But the same thing that I applied in chapter 1 when dealing with that integral approximation applies here. The same principle. We can get a nice approximation of this guy, asymptotic approximation, as lambda gets larger and larger. We can control this term, and so that's what we're going to do. Okay, so I can rewrite the integral as a partial sum plus an exact expression of the remainder. So integration by parts technique will always be applied in this way, so far as I understand, and we will always be trying to get an exact expression for the remainder term. Okay. So let's do the base case. Let's do one step, and then you'll see how the procedure goes. So instead of dealing with the full integral, let's deal with the one that doesn't have the prefactor, just this guy. So what we want to do is we realize that this guy can be integrated by itself, right? And we can differentiate this guy 1 over t by itself. So let's set v equal to minus 1 over t and du to be minus e to the minus t dt. We're going to differentiate v, and we're going to integrate this differential u. So we get dv equals 1 over t squared dt. Remember, we're pretending that derivatives are just fractions of differentials. And integrating this differential, we just get u equals minus e to the minus t. U equals e to the minus t. I think I said that wrong. U equals minus, no, sorry, I said it wrong again. U equals e to the minus t. So our E1 integral then transforms like this and like this, right? So a boundary integral term, or a term where we evaluate at the endpoints. So this guy is v, and this guy has to be u. Evaluate it at the endpoints, t equals lambda and t equals infinity. Of course, this really means take the limit. And of course, I get minus the integral of u dv, right? So u is here and dv is here. So those terms go in there. Same limits, t equals lambda to t equals infinity. And what do we notice about the first term in our approximation of this integral here? So out pops 1 over lambda, e to the minus lambda. When I take the limit as t goes to infinity, that guy, of course, goes to 0 in both cases, because I have 1 over infinity and e to the minus infinity, essentially. Make sense?
So we just need to go against our instinct of integration by parts usually.
Yeah, instead of simplifying integration by parts, we're going to try to create powers of the t. Just more and more powers of t in the integrand. So the first step, we get a t squared. Okay. So in the denominator, we're going to increase that power. So that's kind of against what you would think to do. Okay. Instead of simplifying, you're going to make more complicated. Now, this term here leads to, I could stop at this term and say, actually, that this term here implies that E1 is asymptotic to this approximation. I'm not sure we actually do that, but you can do that. Now what I want to do is, okay, so what you can do at this stage is you can approximate this integral. And I'm going to show you how to do that, but I'm going to do it in a completely general way. Okay. Now, if I want to go on to the next step, so this is one step of integration by parts. The next step of integration by parts would be to identify this at, well, minus this guy as v and minus this as du, right? And then do one more integration by parts. And what that's going to do is create a second term in my asymptotic expansion, plus an integral which gets even more complicated, but I get a t cubed in the, where I get a t cubed in the denominator. Okay, so that's the asymptotic process that you get. And I claim that that ends up with something which looks like this. Okay, if you continue on. Now, there was no lambda e to the lambda term in that in the integral on the second page, and that's because I was only dealing with this part here. You can add it back just through multiplication. Okay, so that's where that guy comes from. And of course, I can take it out of this term, okay, which is what I did. Now, have a look at what that remainder term looks like. If I want to show that I have an asymptotic expansion, what I do is I look at the highest order term that appears here. That's going to be lambda to the minus n plus 1. So I want to show that this remainder term is consequently little o of that term. As lambda gets large. If I can show that the error, remember this measures the difference between I and Sn minus 1. That is the error. So if I can show that that error is little o of lambda to the minus n plus 1, then I'll have shown, and I can do that in general, then I'll have shown that this guy has the asymptotic expansion given by terms which look like that, which is just this. So that's what I aim to show. This is little o of minus capital N plus 1. Or in other words, Rn is little o of 1 over lambda to the n minus 1 as lambda goes to infinity. So what does that mean? That means that if I multiply by lambda to the n minus 1, then this limit is 0 as lambda goes to infinity. Now, how can I prove that? Let's do some estimation with our remainder term. Remember what our remainder term looked like. It was kind of awful looking. Has all this business in it. If I take the absolute value, of course, that goes away. Can't do anything with absolute values with that, but they're nice and positive. Take absolute values of this integral, that can come inside. But you notice that this integral already has a positive integrand, right? E to the minus t, that's positive. T to the n plus 1, that's positive, okay? So when I take the absolute value of that, it's already positive. There's nothing happens. Okay, so that's why you get equality here. You don't have to really even worry about bringing the integration inside. All right, now, but what I notice is that if I look at this term here, 1 over t to the n plus 1, that's a decreasing function, right? As long as n is greater than 0, that's a function which is decreasing and pretty rapidly. So if I look at, so let's plot that, 1 over t to the n minus 1, right? On the t-axis here. Yeah, plus 1. I was confusing this power here with this power. Okay. So either way, they're decreasing functions. So this function for t greater than lambda is less than this value. So that value there is what? That value is 1 over lambda to the n plus 1. So I can remove that from the integral and replace it with something that is bigger than that. So I can take this 1 over this power, or the 1 over this this function here, and I can replace it with something which is bigger. What is that something which is bigger? It's 1 over lambda to the n plus 1. What remains is something that can be exactly integrated, e to the minus t, and then I can evaluate at lambda and infinity. The evaluation at infinity is 0, And so the evaluation at lambda is the only one that contributes, and it contributes in e to the minus lambda. And notice that I get a cancellation here, right? So that's actually important. And I get that this remainder is less than this this value. Now, the size of this n isn't so important. I can just call that a constant. And in fact, I'll do that often throughout the next few slides. I'll just replace this with a constant. I won't worry about the fact that it's some number. All they care about is the size of that power. Now, I wanted to show that this guy, which is estimated by this, is little o of 1 over lambda n minus 1. And I've got just enough room to show that because I have one less power here. So what I need to show is that limit as lambda goes to infinity, lambda to the n minus 1 power times r to the n of lambda is equal to 0. And why will it be true? That's because I can estimate the size of this guy, take the absolute value if you want. This guy is going to be less than, in absolute value, lambda n minus 1 over some constant that don't care what it is. Actually, in this case, we can put it in n factorial, right? Lambda n. Okay, so this guy is going to dominate, the one in the denominator, right? Because I get cancellation. As lambda goes to infinity, this goes to 0. So by the squeeze theorem, this limit has to be 0. Okay, it doesn't matter. This guy can have a sign. This guy can have a sign which is positive or negative. I don't care because I'm estimating the absolute value with this. Okay, so all I needed to show is that upper limit goes to 0 as lambda goes to infinity, and that by the squeeze theorem forces this guy to go to 0 as lambda goes to infinity. Okay, so if I can show that, then I'm done because that is just this, and I have my asymptotic sequence. Remember what it means to be an asymptotic sequence. I have to show, I look at the n minus first partial sum. What's the asymptotic sequence element involved with that highest order term in that sum? It's going to be lambda to the, or 1 over lambda to the n minus 1, which is lambda to the minus n plus 1. So I have to show that the error term or the remainder term is little o of lambda to the minus n plus 1. That's just using the definition of asymptotic convergence. Okay, that's what I did. And so as long as my induction step, so I only did one step in the proof. As long as the induction step is correct, and I really do have this type of expansion, then I've shown what I wanted to show. So it only remains for you guys to fill in the details of the induction procedure. But you'll see, we'll do this enough times that you'll see how it goes, and it'll become sort of second nature. So that's a proof by a calculation. That's how most of the proofs will go in this course. There are some consequential theorems whose proofs aren't that simple, but basically most of the theorems in this course are going to be proved by calculation. Not a ton of deep theory, but just calculations which show the conclusion. So I might write things like proposition and lemma and theorem, but you don't have to be scared away by those things. All you have to think about is how do I do the calculation which shows the result? Let's consider something called the error function, the ERF. ERF of lambda is defined as, should put it defined here.
This is the first time I hear you say ERF.
Yeah.
How about a complementary error function?
Oh, I don't know. Yeah. ERF. Or you asked me today, how do you pronounce
Jensen.
Jensen's inequality?
Yeah.
Jensen or Jensen?
Yeah.
So how do you say the error function? ERF or ERF? I don't know. Again, it depends on where you're from. The ERF is defined as this exponential integral. So notice again that it's an integral that has an exponential, and one of the limits, upper or lower, is equal to lambda, the parameter that's going to get large. So I want to estimate the error function as lambda gets larger and larger, larger and larger. Okay. I can also estimate as lambda goes to minus infinity, turns out as well, using a similar procedure. Now, this integrand is complex analytic, meaning that it can be represented by its Taylor series expansion. So I could substitute in this Taylor series for e to the minus t squared, and then I can integrate that actually term by term. So you're allowed to do this actually because this has an infinite limit of convergence and converges absolutely in its radius of convergence. So I can actually show that the error function has this convergent series expansion. So this guy does converge. And again, I could work with lambda being negative. What we're interested in here is lambda is positive. This converges for all finite lambda. Could be up to 100 billion, doesn't matter.
I have a question.
Okay.
So actually, I encountered this question when I was doing the homework. Is it necessary that the asymptotic series must be the Taylor series? Like,
no, it doesn't have to be the Taylor series.
but asymptotic series itself is unique because we show that theorem.
Yeah.
The coefficient can explicitly count.
So if you have a Taylor series expansion, then that should be the asymptotic expansion. In fact, Taylor is the usual place to start when you want to show something is asymptotic. Start there and see if it works. Okay, so any convergent Taylor series should be an asymptotic series approximation as well.
How about non-convergent series?
Non-convergent? Well, we're going to encounter those all over the place.
Oh,
Yeah. So, I mean, well, I guess,
but for our understanding, I feel like the convergence doesn't really matter.
let's see. No, it's not going to matter. And I'll show you that momentarily. So let me back up. So if I have an analytic function, that means that it really is equal to its Taylor series expansion, infinite series expansion. And that infinite series expansion is the asymptotic expansion. Okay. Now, if I compute the Taylor polynomial and take it out to all orders, then but the Taylor series doesn't converge, that may or may not be an asymptotic series approximation. It depends on what context you're looking at. Generally speaking, it is.
I mean, okay, let me try to think another way.
Okay.
For example, let's pick epsilon, like the epsilon convergence. So we're going to zero. So we have epsilon squared, epsilon cubed. So that is an asymptotic sequence by definition. And even if my Taylor series is not convergent in the whole space or some space, but the uniqueness, because we already fixed that particular asymptotic sequence, it should be.
It sounds like it should be.
Yeah, I think so.
If I understand what you're asking.
Yeah, if we formally choose like the asymptotic sequence, be it convergent or non-convergent by the definition and by the uniqueness, I think they should be the same.
Well, if you do find you have an asymptotic expansion, and then you find another asymptotic expansion, there's some candidate, then yes, they do have to be unique as long as and this is the key, as long as the asymptotic sequence is the same.
Yeah. That's what I'm saying.
Then yes, I mean,
Maybe
if you find two asymptotic sequences, then they have to be the same. Yeah. Okay, so the story behind this and the problem with this infinite series is that it's very slowly convergent for even modestly large values of lambda. And so if we're really looking for an asymptotic approximation of the error function as lambda gets very large, then this is not going to be very helpful, because the convergence of this gets really bad as lambda gets large. So that's why asymptotic expansions tend to be favorable. So even though they are not convergent series, they can lend themselves to more useful approximations for large values of lambda. So let's convert the error function into something which is immediately amenable to our analysis with integration by parts. So remember, integration by parts worked as long as the lower limit was lambda and the upper limit was infinity, as long as we were dealing with these exponential integrands. Now, you can shuffle things around so that maybe you could do integration by parts where the upper limit is lambda, but we already have some experience dealing with this guy. In that case, the lower limit was lambda. We had experience dealing with an integral where the integrand was an exponential. Now, why is this true? How can we do this conversion? Well, this hinges upon the fact that this following Gaussian integral has the limit or the value pi, square root of pi over 2, which you can check kind of easily. Usually, these Gaussian integrals, you're probably familiar with these, are sometimes tabulated in terms of the integral from minus infinity to infinity. So we have our Gaussian, and the Gaussian dies off fast enough so that no matter what, both sides are integrable. So you can, and you'll usually see it written as e to the minus t squared dt is equal to square root of pi. But in any case, we're dealing with an integral over the interval 0 to infinity. So if we write this integral in this place here with a prefactor of 2 over square root of pi, then by the definition of the error function, it's clearly just equal to 1 minus 2 over square root of pi times the integral lambda to infinity of e to the minus t squared. So if we want an asymptotic approximation of the error function, it suffices to get an asymptotic approximation of this integral. And this guy, surely we can deal with using our methods that we've introduced so far. So let me see, what was our first integral? Our first integral was one which looked like this, right? E to the minus t over t. This one doesn't actually have that form, but it has an exponential where the power is minus t squared. We can think about this as just being over 1 here. So it's like t to the 0. So let's do one step of integration by parts on that integral. What I'm going to do is write something here so that this differential becomes exactly integrable. So to do that, I write minus 2t quantity, and I have to divide by that same quantity. Okay, so then this differential becomes exactly integrable. Okay, that's what I'm going to call du. If I integrate that guy, I get u equals e to the minus t squared, obviously. This part I'm going to treat as my v, and I'm going to differentiate that, and that's going to make the integrand worse every time. So if I differentiate v, dv dt is equal to 1 over 2t squared. So dv is 1 over 2t squared dt, treating the derivative as if it's a fraction of differentials. Okay? So I'll assume that you can do these simple derivatives and antiderivatives. So our integrand from above then is equal to 1 over minus 2t e to the minus t squared. That's because this is just going to be v, and this is going to be u. I have to evaluate at the two endpoints, t equals lambda and t equals infinity. When I do that, I get 1 over 2 lambda e to the minus lambda squared. The order reverses because remember the limit at infinity is just going to be 0. And this guy is finite, but that comes with a minus sign. So altogether, it's a plus sign. All right, now I'm going to play around with my integrand again. I want to do integration by parts on this guy. So let's get it into a state where it's clear what I'm going to do next. Well, what I want to do is get an exact differential here. And so I multiply by minus 2t squared, same as I did previously. I have to also divide by that same amount. So that turns this negative integral into integral from lambda to infinity, 1 over 4t cubed minus 2t times e to the minus t squared dt. So this is an exact differential. So I'm going to define that to be my next du, and I'm going to define this guy to be v. Of course, this is the same du that I had above, and it's always going to be the same. Du is always just going to be this, and v is going to change according to the step. So let's do a second integration by parts. Second verse, same as the first, right? It's just like a song that is repetitive. So v is equal to 1 over 4t cubed. Du is equal to that exact differential. So dv is equal to minus 3 over 4t to the fourth power, and u is equal to e to the minus t squared. All right, so we leave our first term alone that we derived. And we replace the integral, which is this integral here, with the integration by parts formula. I do v and u evaluated at the endpoints. And now I have a new integral, which is going to be minus u dv. So minus this integral pairing right here. But the minus can't that I have with that integral destroys this minus, and so I get a plus. Integral from lambda to infinity of this integrand here. And of course, when I evaluate this guy at the endpoints, the upper limit is just going to be 0. And the lower limit, lambda, changes the sign here. So I by replacing t with lambda, and I get this term. All right, so look at this progression. This term stays the same. This term stays the same, right? But the power on my lambda is growing each time. So this is starting to look like an asymptotic series. Now notice that it's an interesting asymptotic series from the point of view that the powers involved are going to be 1 and then 3. So it skips 0 and the power 2. And of course, if we wanted to stop with this being our asymptotic approximation, we can just estimate the size of this integral. But let's do a third integration by parts. All right, so our last integral, we fixed it up before we exited. How did we fix it up? You multiply by minus 2t and you divide by the same thing. That makes the denominator minus 8 t to the 5th power. And so v becomes 3 over minus 8 to the t to the 5th. du is that same exact differential as before. I integrate that to get u. When I take the derivative of v with respect to t, I now get 1 times 3 times 5. I'm going to start tabulating these guys. You'll see how they come out. You just get the product of odd numbers. In this case, the third odd number, right? The product of the first 3 odd numbers over 8t to the 6. All right, so that's the integral that I had. I'm going to replace that now with the appropriate u and v. I do the boundary evaluation. You know, you can see now that I'm alternating in sign, plus, minus, plus. The powers increase by a factor of 2 each time. So lambda, lambda cubed, lambda to the 5th. And the coefficients are 1, 1, and 1 times 3. And the next one's going to be 1 times 3 times 5. And the one after that, 1 times 3 times 5 times 7, for product of the first 4 odd numbers. So I get those first 3 terms. This is my remainder term, but before I exit, I'm going to fix it up, make it into an exact differential, and the game continues. All right? Does that make sense? All right, now if we wanted to stop here, let's see, can we stop there? We can do one more. Let's do one more. And we'll get a 4-term approximation with a remainder. So the 4-term approximation that we're going to get is this guy. 4 terms. Leading order, correction, 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 okay? So even though this is up to the 3rd order here, I call this the 4-term approximation. Okay, so, and by the way, you see how these powers are growing. Okay, so keep that in mind. 2 squared, 2 cubed. Okay, so I can take out this common factor, and then I have this expansion plus a remainder. And you can imagine if I do the next step of the integration by parts, it's not hard to believe that that's what the remainder is going to look like. Now I can estimate the size of this guy. Let's stop as if we were going to do, we'll just leave it at that asymptotic approximation there. So if that's true, all we want to show then is that this minus this is little o of the last term. Okay. But let's estimate the size of R4 before we think about that. How can we estimate the size of R4? Here's R4 if you believe it. So take absolute values, move the absolute values inside if you need to. Remember, we're going to use our usual trick. 1 over t to the 9th. That's going to be a decreasing function. Decreases really fast. And here at lambda, if I approximate this guy by a constant, that value is going to be 1 over lambda to the 9th power. So that guy comes out with all the other constants. And so that's where that comes from. What I'm left with inside is integral from lambda to infinity. Now I fix things up so that this guy is an exact differential again, or almost an exact differential. It would be exact if it was a minus sign, but I want the integrand to be positive when I take absolute value, right? But in any case, when I integrate this, this is just going to be e to the minus t squared, evaluated with a minus sign, evaluated at infinity and lambda. The fact that the first evaluation is going to give 0 and the second evaluation is going to bring a minus sign gives me my minus minus, which gives a plus. And so that's why I get this term. All right, now all I want to show then, if I want to have the beginnings of an asymptotic expansion, is to show that this guy is little o of what? So this guy should be little o of whatever term appears last here, right?
But you have a lambda.
So yeah, right. So I have 6, but an extra one here. And don't forget, this guy comes along as baggage. That is also part of your asymptotic sequence. So I have to show that this guy is little o of e to the minus e to, oh gosh, e to the minus lambda squared, lambda to 7th power, right? Now, is this term of that little o nature? Yeah, it is, right? Because I have to show that the limit, to prove that, I would have to show that the limit of lambda to the 7th, that's a weird 7, looks like a T, lambda to the 7th over e to the minus lambda squared times e to the minus lambda squared over lambda to the 9th as lambda goes to infinity. Let me do some separation here. So okay, so I have to show what? That this guy is equal to 0. Is it equal to 0? Yeah, no problem, because this cancels with that, and this cancels, and all I'm left with is a 1 here and a lambda squared in the basement. So it's 0.
So the remainder of the area is kind of smaller than the largest term in.
Yeah. Mm-hmm. Right. It's dominated by that last term. That's how you can say it. So whatever term appears last here or last here, of course I have to take into consideration this and this as well. That has to be, this term has to be little o of that as lambda goes to infinity. Okay, so this term here has to go to 0 faster. Okay, that's what it means to be little o. So I could stop there, right? And say, let's see. Well, I guess I already said this, right? So I wanted to show this. And of course, that means that. But this is clearly true because of that estimate that I already produced. Okay, and I can use the squeeze theorem. Right? Does anyone need to see or want to see all the details of that? Does everyone know what I'm talking about when I say the squeeze theorem? Okay, I'm going to assume you do. I could stop here and don't be ashamed to ask a question, okay, if you don't understand something. Okay, so I use the squeeze theorem to show that this is true. Or in other words, that this limit is true. By the way, that should be if and only if. Okay. Okay, so I have the 4-term approximation. Right? I just showed that. So
Hey,
I
Dr.
could
Wise.
really, yes, question?
It looks like we've got a comment in the chat.
Comment in chat, thanks. Okay, someone would like to see that. Okay, let's slow down and take care of it then. All right, so I want to prove this using this. How do I do it? Okay, so I'm going to take the absolute value of this thing. Well, actually, I don't want to. Okay, so let's look at the absolute value of that. R4 lambda e to the minus lambda squared over lambda to the 7th. Okay. So if I want to show that this guy here, if that limit is 0, here's one way to do it. I can show that its absolute value is 0. Do you agree? If I can show that the absolute value is 0, then the original sequence or the original limit is going to be 0. Does everyone agree with that? Okay, so I'm going to start there, and I'm going to show that the limit as this guy, lambda goes to infinity, is equal to 0. That's how I'm going to prove this. Actually, this is true if and only if that's true. So how can I do that? Well, I'm going to take a sequence which is bigger than this guy. So what sequence could I find which is bigger than this guy? Well, I already know that this limit or this estimate holds according to my previous calculations. Remember, these are proof by calculations. Proofs by calculation. So I already proved this limit, and all I used, the only technology I used here is I used this upper bound for 1 over t to the 9th. That allowed me to bring that upper bound out, 1 over lambda to the 9th. Then I used the fact that what remained was an exact differential, or almost up to a minus sign. I could integrate that exactly, and I ultimately get this. Okay, so I have this upper bound for R4 lambda, which is stated right here. So now I can show that then R4 of lambda times lambda to the 7th over e to the minus lambda squared. That's what I have. That's what I have up here. That's just the same thing as that, right? These two things are exactly equal. All I did was invert this fraction, right? If I'm dividing by a fraction, I invert and multiply. So that's just that. But now, because of this bound down here, I can say that that's less than constant e to the minus lambda squared, lambda to the 9th, and lambda to the 7th, e to the minus lambda squared. Okay. So I get cancellation, cancellation. This becomes a 1. This becomes lambda squared. And so I can say that this thing here, all that, is equal to c over lambda squared. Now, the squeeze theorem says if I have something like that, I have an upper bound on this guy, which goes to 0 as lambda gets large. This goes to 0 as lambda goes to infinity. Then that says that it's squishing this guy, squeezing that to 0. Okay, so notice I have a function which beats this function. This function is bigger than that. That's what greater than or equals means. That function is going to 0, and it beats this function. Right? So this guy, of course, this guy is greater than or equal to 0. So squeeze theorem means it gets squeezed between 0 and 0. Okay? In sequential terms, if it's a sequence of things, we say that if we have a sequence AK, which is bounded below by 0 and bounded above by a sequence BK, and we know that BK goes to 0 as K goes to infinity, then that implies that AK goes to 0. It gets squashed to 0. Okay? That's why it's also sometimes called the Mack truck theorem, right? So here's a brick wall, and here's a Mack truck, right? It's a badly drawn truck. I don't know. It's a Cybertruck, Tesla Cybertruck. And there's some entity here, AK. This is BK. This is the 0 brick wall. This guy's driving into that guy and squashes it down to 0. Okay? It's the same principle that's going on here. Okay, this Cybertruck is cramming this Prius against a brick wall. Okay? This guy goes to 0 and it beats this guy. So that means this has to go to 0. Okay? There's a lot of black ink on the screen, but does everyone get that? Does everyone understand that? Okay, good. So I just showed that remainder term, remember the remainder term really is the error. It's the difference between that and that. I just showed that remainder term has that little O nature. Okay, so that means that I can really say that this guy is asymptotic to this, to that 4-term expansion. I could keep going. I could add one more term to my asymptotic expansion, and you can already see the pattern. You can recall the pattern. The next term is going to be coming with a plus sign, 1 times 3 times 5 times 7 in the numerator. In the denominator is going to be 2 lambda squared quantity to the 4th power. And so I have to show that this term here times this term, the combination of those two, is little o of e to the minus lambda squared over lambda to the 9th. And of course, that's going to be easily true. The power down here is going to be 2, 4, so that's 8, 9. And the remainder I can show is going to be like lambda to 1 over lambda to the 11th, something like that. Okay. So it's another calculation. You have to do one more step and calculate the remainder one more time and do it. But we can just do this in general terms, right? Now, what does it mean for us to have a proposition here? It's again a proof by a calculation. What's missing is you have to do the induction step to get that, or to apply integration by parts in a sort of general way. If you're not familiar with induction, I think everybody has a really good commonsensical understanding of what induction is. You assume that you have that the nth case works, and then you show what you know by the mechanics to show that the n plus first case works. But if you have any questions, send me an email and I'll be glad to write out the details of the induction proof. Okay, I'll be glad to supply that. How do I get this to hide? Does anyone remember? Oh, well, it's not. I guess it's supposed to just fade away, but oh well. It did. Okay, great. I guess once I checked the chat, it went away. Okay. All right, so remember, don't be scared of a theorem, lemma, or proposition most of the time. Sometimes you have a right to be scared. And in fact, once we start talking about Watson's lemma in the next lecture, you'll see that these proofs can get complicated, but really it's all calculations. So the proof will get complicated, but only because we have trouble taking care of all of the terms that start floating by. And you'll never be asked to reproduce a proof that is super long and complicated. You'll only be asked to do proofs that are really computations. Okay, so here's the integral that we have to start with. Remember, it's the integral that, if we can estimate this as lambda gets large, gives us our estimation or our approximation for the error function, the erf, as lambda gets large. So we can show that this guy has this asymptotic series expansion. And all of the terms are the terms that we've faced before. The term that can be extracted and it multiplies everything else by the distributive property, e to the minus lambda squared, 2 lambda, that's the same. These BK coefficients, remember that those were the products of the odd numbers up to a certain value. So BK means the product of the first k odd numbers, right? Minus 1 to the k, you understand that. That's just coming from the fact that we're having alternating sign. And every time we produce another term, we produce another power of 2 lambda squared to the k power. Okay, so the asymptotic expansion then ends up looking something like this. This is another way of writing it. If you want to write an asymptotic expansion, you don't have to use a summation with an upper limit being infinity. You can use your good old-fashioned dot, dot, dot to indicate that things go on and on forever in this fashion. What do you think? Does this thing converge? We should have a little quiz at the end, like, does it converge? Does it converge? I'm going to bet no. Why? Because BK is looking an awful lot like a factorial, right? It's getting too large to be controlled by the thing in the basement. So probably this guy diverges like crazy. We already had a convergent power series approximation of the error function, but we argued that it was more or less useless because it converges too slowly for modest values of lambda. I'm going to guess, and I think I'm right, that this guy diverges in a big way. But remember, asymptotic approximations are used in the following way. We stop at a certain k, and then we take lambda to get larger and larger, and we show that the approximation as lambda gets larger gets better and better. So in fact, what you usually do if you have an approximation like this is you stop and you disregard these and you send lambda to infinity, or you look at lambda and it goes to infinity, but you don't keep going. You don't keep adding terms this way. All right, so, and then knowing that gives us an asymptotic approximation for the error function, which actually is useful in calculations for large lambda. All right, so again, I'm leaving some things to the imagination. I claim that you can show that the integral can be integrated by parts any number of times, and you get the nth partial sum to be something which looks like that. That's believable because we've already produced that. And the remainder term is something which looks like this, which is again also believable. All right. Now, all we have to do then is look at the last term that appears in the series approximation. What is the size of that guy? It's going to be e to the minus lambda squared. Lambda, I can just throw away constants. You don't have to keep track of constants. And 1 over lambda to the 2k power. Right? So this is the same as e to the minus lambda squared, lambda 2k plus 1 power. So I have to show that the remainder is little o of that guy. I have to show this hopefully is little o e to the minus lambda squared, lambda 2k plus 1, as lambda goes to infinity. That's what I have to show. And if I can show that, then I have my asymptotic approximation. It should be no surprise that that's true. So here's our remainder. And we can estimate this on the upper side, I claim, by some constant. It depends on m, but otherwise it's just a throwaway because I'm going to fix m. Okay, and take lambda large. So all I need is really the dependence of the size of this guy on lambda. E to the minus lambda squared and lambda over 2m plus 1. Oh, I was wrong here, right? So the highest order term ends in an m, not a k. So that should have been an m. Okay, so the power on that guy should be lambda 2m plus 1. But in my remainder, I get something which is clearly under that, or which is going to 0 a lot faster than that, I should say, because it's in the denominator, it has the power of lambda of 2m plus 3. Right? So I'm going to use the squeeze theorem again, my Mack truck theorem, or the Cybertruck theorem. And I need to show that that term here is little o of this term. which it is. Because when I invert this guy, it's going to appear in the numerator, and the power here is going to dominate. So as lambda goes to 0, this guy is going to go to 0, no problem. So my remainder term is clearly going to be little o of e to the minus lambda squared, lambda to 2m plus 1, because this power here is 2m plus 3. It's bigger than I need. Actually, what would I need? I just need this guy to be 2m plus a little bit. It could be 2m plus a half or 2m plus a quarter. I just need a little bit of extra, okay, what's called an epsilon of room to drive through. I just need this to be a little bit bigger than 0, but it's a lot bigger. 3 is, 3 is way bigger than 0. Or no, sorry. I just need this guy to be bigger than 1. Yeah. So let me restate that. This number that appears here just has to be just bigger than 1, and it's clearly bigger than 1. It could be a 2, it could be 1 plus 0.1. Okay. All right, let's do another one, if you're not getting tired of these already. Okay, we'll do this one in 3 minutes, I promise. So let's have a look at this exponential integral here. I have lambda's integral from lambda to infinity e to the minus t to the 4th power. And of course, I could rewrite this so that I could input a power series expansion, which converges absolutely and has a radius of convergence being everything. That's true of e to the any power there, any polynomial power, because it's an analytic function. So, but the problem is the same words of wisdom can be applied here. This power series is going to converge way too slowly to be of use. So that's why an asymptotic series expansion is going to be useful to us. Now you start with that integral. You multiply whatever you need to make this into an exact differential. And then, of course, you have to divide by that. And so you get this integral, obviously. And I'm not sure why I brought the 1/4 out. I guess I could have just left it in. You get, on doing one step of integration by parts, you get this term, and that's going to be your leading order expansion, okay? In fact, you only have to do one step of integration by parts usually to get a leading order asymptotic expansion. And once you have that, then you're basically done, okay? Well, if one term is good enough for your approximations, and oftentimes it is. All right, so my first term is that. If I want to get a second term, I'm going to have to do integration by parts on whatever remains. And so what remains is this guy, and so I can operate on that. Of course, if I want to stop with that one term approximation, no problem. I can just deal with the remainder. In fact, you can show pretty quickly that the remainder is going to be bounded by a constant. So this is what I'm going to call the remainder here, this whole thing. In absolute value, it's bounded by a constant, e to the minus lambda to the 4th over lambda to the 7th. And because this term is a whole lot smaller than that, well, these powers, let's see. Yeah, this power here, okay, this guy is a whole lot smaller than that. That's all I need to show that this is asymptotic to that. So that's my single one-term or leading order approximation. And of course, you can go on and on like this, right? This one, same sort of style. You're going to do integration by parts, get a remainder, estimate the size of the remainder, and that generates, that tells you whether or not you have an asymptotic expansion. And the fact that that remainder keeps getting smaller and smaller and smaller in some predictable fashion is what gives it to us. And so the asymptotic approximation I get in this case is just going to be this. All right, so we'll end here. If you find any errors in the notes, kindly let me make me aware of them. I'd love to fix those. The notes, the lecture notes, follow the slide deck for the most part, except that I rearranged the order a little bit, but I haven't yet gotten around to rearranging the order in the lecture notes. But you can see now the lecture notes go all the way up to this method called the method of steepest descents. So that's another couple of chapters. If you're interested, you could read ahead. But in any case, send me any questions you have. Come visit me in office hours on Friday if you have any homework questions. And if you have or find any errors in the lecture notes, kindly forward those to me by email or in person, and I would love to get those things corrected. So with that said, I will see you guys on Thursday. Have a nice day.